The second speaker of the session is Professor Yiwen Chu from the ETH Zurich in Switzerland. And the title of her talk is Quantum Information Processing with Mechanical System. Welcome, Professor Chu, and the screen is yours.
All right, thank you very much for the introduction, and good morning from Zurich. First of all, I would like to thank the organizers for inviting me. So I'll be telling you today about some of our work on using mechanical systems, the motion of objects, to control and to store quantum information. Okay, so just a brief outline of what I'll talk about. So first, I'll briefly introduce this field called circuit quantum acoustodynamics. It's very analogous to the field of circuit quantum electrodynamics, which maybe some of you have heard about. And I'll tell you about what it is and how it works very quickly, just so we're all on the same page. And then I'll talk about how we can use it to make quantum mechanical states of motion or of sound in our case. And then we'll talk about what these states are useful for. All right, so let's start with the basics. So as I mentioned before, circuit quantum acoustodynamics, or circuit QAD, is very closely related to circuit QED, in which of course people have developed a large range of very sophisticated tools for controlling the quantum states of these complicated electromagnetic systems. All right, and the idea is that we want to use those tools now to control a whole new degree of freedom, which is mechanical motion. And that can take many forms, and I've just drawn some cartoons of a couple of them here. All right, and the goal is not only to use these tools to now bring these objects into the quantum regime and to control their quantum states, but also see how these new mechanical objects can bring new capabilities to our quantum circuits, whether or not we can use them as new circuit elements for quantum information. Okay, so very briefly, how does this work? Well, in a simple picture, you can imagine some sort of circuit. In this case, I'm drawing the circuit diagram for a typical superconducting qubit, which consists of a nonlinear inductor in the form of a Josephson junction, connected to a capacitor. Okay, so this forms an anharmonic LC resonator that we usually use as our two-level qubit. Okay, so as with most capacitors, there's some electric field that is associated with this capacitor, and what we can do is we can put our mechanical resonator, our acoustic resonator, inside this field and add in a piezoelectric material, which of course converts electromagnetic energy into mechanical energy. All right, and that's how these two systems get coupled. If we want to be a bit more quantitative, we can write this down in terms of the Hamiltonian of the system, which is very simply just stress times strain, which gives you the energy of the interaction. And we can write this in terms of the quantum mechanical operators that describe our electromagnetic mode, in this case B, and then our mechanical mode, which is given by A here. Okay, and they are coupled together through this bilinear interaction with a strength that is given by G. So G is the coupling strength, which, as you can see here, depends on things like the piezoelectric constants, the material properties, and also things like the electromagnetic field and the strain field of the qubits and of our acoustic resonator. Okay, so this is one way of building such a circuit quantum acoustodynamics system. And there are actually other ways. So here I'm giving another example, which doesn't actually use piezoelectricity. Okay, so what does this look like in reality? So I've shown you a couple of cartoons of these mechanical resonators. And here I'll just show you three more specific examples of recent experiments that have been done in this field. So the first one uses a phononic crystal. So it works in the same way as the photonic crystal. You have some sort of periodic structure that confines now not light, but instead sound or acoustic waves. And then we have also a surface acoustic wave, which, as its name implies, involves waves, acoustic waves traveling along the surface of a material. And then a bulk acoustic wave, which is just sound waves inside the bulk of a material. Okay, and this is what it looks like when we put these objects together with our quantum circuits, right? So you see on the left here a phononic crystal structure, which has a electrode on top of it that allows it to couple to the circuits. In the middle here is, again, a lithographically defined electromagnetic circuit that couples to surface acoustic waves. And what I'll focus on today is our work, which uses these bulk acoustic wave resonators. And here is just a cartoon drawing of that, where we have our superconducting qubit on the surface of a crystal, and then we couple that to a what's called a high overtone bulk acoustic wave resonator, or H bar, using, again, a piezoelectric material. Okay. So this is just a cartoon. Here, let me show you a bit more, slightly more detailed drawing of our device, where you can actually see all the different parts. So what we have here, for example, is on the bottom, we have, again, our wafer made out of, in this case, sapphire, on which we fabricate our superconducting circuits. And then we take another piece of sapphire, actually, and we also make our acoustic mode out of that, our H bar. And what that is you can think of as basically a Fabry-Perot resonator that traps sound waves, right? And just like in an optical Fabry-Perot resonator, what we have are two mirrors, which are now just the surfaces of the crystal, one of which is flat and the other is slightly curved, in order to confine a stable acoustic mode. Okay, so then we take these two things. And also we have this yellow color here represents the piezoelectric material, which in this case is aluminum nitride. Okay, and then we take these two pieces and we basically just stick them on top of each other with some glue, basically, and a spacer to make sure that we keep a particular desired distance between the two. Okay, all right. So now what can we do with such a device? So I showed you this Hamiltonian earlier, which basically allows us to swap energy between our electromagnetic mode, our qubit, and our acoustic mode, our phonons. All right. And so what we can do is, I mentioned before, our qubit is an harmonic resonator, right? So we can isolate two energy levels of this quantum system. On the other hand, our acoustic resonator is a harmonic oscillator, right? And so it has the usual evenly spaced energy levels. So let's say both systems start out in the ground state, which they do because these are gigahertz frequency modes, and we put them inside a dilution refrigerator at millikelvin temperatures. So what we can do is we can come in, let's say, with a pulse of microwaves, and that excites our electromagnetic mode, our qubits. And then due to this coupling that I showed you earlier through the piezoelectricity, what will happen is this energy will swap back and forth between these two systems. Okay, and then eventually it will decay out through some other channel. Okay, and this is exactly the behavior that we see. What you see here are vacuum-Rabi oscillations of the energy swapping back and forth between our qubit and our acoustic mode, right? And here in the middle is where the two systems are on resonance. All right, and just to give you a sense of some of the other parameters of the system, as I mentioned, both modes are in the gigahertz regime. And the important thing to notice here is that in order for this process to happen, as I've described it, what you need is that the strength of this interaction, what I'm calling G naught here, for a single excitation has to be larger than the rates at which energy can decay out of the system using in other forms. Okay, all right. So I've shown you sort of already some basic quantum operations, right, on acoustic waves using our superconducting qubits, but we can go further and do some more sophisticated manipulations. But first, let's understand a bit better what the mode structure of our acoustic resonator is. So what you see here is a picture where you have, in this case, 4 of these vacuum Rabi oscillations that I just showed you on the previous slide. So that's the same thing, right? And they are spaced by about 13 megahertz, which is just the free spectral range of our acoustic Fabry-Pro resonator. Okay, and then in between, you see some other features, and those correspond to, again, just like in an optical Fabry-Pro resonator, you have higher order transverse modes, and so these the oscillating features that you see here correspond to the fundamental Gaussian mode, and those other smaller features correspond to the higher order transverse modes. And we can figure out what their frequencies are and figure out what their mode shapes are. But one important thing to want to emphasize here is that you see that our qubit, just by tuning its frequency, we can have it talk to a bunch of different phonon modes. All right, and this is going to be important later on. Okay, so now that we understand the mode structure of our system, and we know where to park our qubit so that it interacts with our acoustic mode, we can do some more complex operations on our phonons, and this again is borrowing tools from Circuit QED. And first of all, what we can do is, for example, put more and more excitations into our acoustic resonator. Right? What we can do is what I've already shown you, which is to excite our qubit and let the energy swap over into our phonons. But we don't have to stop there. We can keep going. We can continue to excite our qubit and let the energy swap over, and so on and so forth, and climb up this energy ladder, right? So G and E here are the ground and excited states of our qubit, while N is the number of phonons in our system. All right, and we have to be careful that, of course, the coupling strength gets stronger with the square root of the number of excitations in the system. And at the end, if we want to make sure that, say, we've created a state of 3 phonons in our acoustic resonator, what we can do is actually take advantage of the fact that this coupling strength scales with the number of excitations. Right? So if we, again, let it just interact with the qubits, you'll see these oscillations of the energy swapping back and forth. But depending on how many phonons are in the system, this oscillation is going to be at a different frequency. Right? And the frequency is going to be proportional to the number of phonons. And in general, of course, we're not going to necessarily prepare a state of just 3 phonons. It's going to be some superposition or mixed state potentially of these different Fock states, phonon numbers, right? And we can see those frequency components when we let our qubit interact with our phonons. And that is indeed what we see, right? So if we go higher and higher up the ladder, if we take up to 7 steps up this ladder, we see that these oscillations get faster and faster. Okay, and as I mentioned, we can sort of decompose the frequency components in these oscillations to actually get a quantitative measure of what is the population in each of these phonon states. So it's kind of a funny Fourier transform, but into these frequency components at scale as a square root of the integers. All right, so if we do that, what we get is just a distribution of populations inside our Fock states of phonons. And you see here that, fortunately, up to a phonon number of about 4, let's say, the majority of the population is in the state that we try to create. And so this tells us that we are able to create sort of some of the simplest quantum states, these Fock states, these states of definite phonon number. However, this does not give us the full information about our quantum system, right? This only gives us the populations, which are the diagonal elements of our density matrix. Now, in order to figure out the full quantum state, what we need to do is tomography on this quantum state. And we're going to do that using something called Wigner tomography. Now, Wigner functions might be familiar to some of you who work in optics as ways to characterize the state of light. And again, here sound is analogous to light, and so we can use the same techniques to characterize our quantum state. So let me tell you in detail about how we measure that in our system. And again, these techniques have been used in circuit QED to measure the state of of electromagnetic resonators. Okay, and so what we do is, let's say we take our probability distribution for the number of phonons in our acoustic resonator. Okay, what we can do is we can calculate something called the parity, which is just the sum of the populations in the even number Fock states minus the sum of the populations in the odd number Fock states. So for this particular case, which is the distribution when we try to create the Fock state 1, what we get will be a negative number. Okay, and we take that and we plot that in the center of our phase space, okay, which are just, you can think of as the position and momentum of our mechanical resonator, or the real imaginary parts of our complex displacement amplitude. Okay, and so since it's negative, it's going to be a blue dot there in the middle of phase space. Okay, what we can also do, is instead of just making our states and measuring the parity, is we can also, in between, perform a displacement of our mechanical resonator, and that just means basically driving it at its resonance frequency, right? And this displacement will have some complex amplitude depending on how hard and how long we drive for and the phase of the drive, and that's going to correspond to some other point in phase space. And what we're going to do is, after this displacement, we're going to measure the parity again, and then we're going to plot the results at that point in phase space. And we're going to do this for many different displacements, like so. Right. And down here is just the expression that expresses the Wigner function in terms of these operations that we're doing here. Okay. All right. And so if we do this for enough different displacements, enough values of alpha, what we'll get now is basically a picture in phase space, right? Which is basically like a fingerprint of our quantum state in phase space. And this is what it looks like, this Wigner quasi-probability distribution for the state of one excitation in a harmonic oscillator. Okay, what you see here is in the middle, the parity is negative because this is a state with one excitation in it. Right, but it has this shape in phase space that allows us to visually represent our quantum state. Okay, and so now what we get when we do this in our experiment. So on the left is just a plot, a theoretical plot. On the right is our experimental data, which is of course a bit more pixelated, but we see that it has roughly the same shape. Okay, and we can do this for other quantum states. For example, a superposition of 0 and 1 phonons, and a state of 2 phonons. And because our Wigner function, Wigner distributions have all the information about the quantum states in them, what we can do is we can take them and we can calculate we can reconstruct what the corresponding density matrix is for these states, and maybe that's a bit more intuitive to understand for these particular states. So for example, here we see that most of the population is in the 1 Fock state, and a little bit of it has decayed to 0, again, because of dissipation in our system. Right? And here you see for the superposition also the coherences that appear in our density matrix. Okay, so this was also sort of to introduce you the basic tools that we now have access to in circuit QAD. And now you might wonder, right, so as I mentioned, we can also do this with electromagnetic resonators. So why would we want to do this with mechanical resonators? And what can they do that maybe electromagnetic systems or circuits cannot do? All right, so let me give you a simple example. All right, so a 6 gigahertz acoustic wave in sapphire, which is the frequency we're working around, has a wavelength of about 1.2 microns. All right, a 6 gigahertz electromagnetic wave in vacuum, right, which is roughly the what we have in our quantum circuits, the wavelength is about 5 centimeters, right? And these length scales also then dictate the size of the devices that we need in order to store these excitations, okay? And I already showed you earlier, right, this picture, right, where in a single mechanical resonator, which is actually quite a bit smaller than our superconducting qubits, if you remember from that cartoon, we have many, many modes, right? We can fit many more of these waves, these standing waves inside of our mechanical resonator because its wavelength is so small, right? And this is, of course, very useful. This fact that phonons can store more quantum information essentially in a smaller volume than photons. And of course, this would be great if you could use this as, say, a quantum memory or some other device that requires you to store many pieces of information in individual locations. Okay, and so that's what I'll talk about for the rest of my remaining time. Just to give you a sense of an example of how mechanical resonators can be used for quantum information. All right, but first let's answer the question of how do you even use harmonic oscillators in general to store quantum information. You may be used to thinking about qubits as storage for quantum information. And you can do that simply by treating your harmonic oscillator states. You can pick 2 levels and use that to encode your qubits. Let's say the 1 state and the 0, the vacuum states, and you can make superpositions, and we've shown we can do that. All right. However, this is a bit of a tricky encoding because you can easily leave your code space, right, because of these harmonic equally spaced energy levels. And in addition, you can't really error correct such a state. As soon as your state 1 decays to 0, you can no longer retrieve the information. However, you might have heard in some of the previous talks on this conference, for example, by Yvonne Gao and by Jonathan Holm yesterday, about a different way of encoding information in harmonic oscillators. And these are called bosonic encodings, which are now being explored in circuit QED and trapped ions. And the idea is you can take advantage of the infinite Hilbert space of a harmonic oscillator and make these more complicated states. And one example is, for example, storing your 0 and 1 in 2 different coherent states of your harmonic oscillator, which just correspond to these blobs in phase space when you talk about the Wigner function. So here is an example of a superposition of 2 coherent states, right? You have these 2 red circles, which correspond to the coherent states themselves, and these fringes tell you that they're in a superposition. All right, and this is something called a Schrodinger cat state, which has been demonstrated in circuit QED, and I believe also in the motional state of a single trapped ion. Okay, and people have demonstrated using these states to do, for example, quantum error correction and to perform operations on multiple qubits. And so our mechanical resonators are equally good harmonic oscillators as these microwave circuits. And so the idea is that maybe we can take advantage of their unique properties. And so just to give you an idea of how that works, right? So our superconducting qubits are basically anharmonic oscillators, as I mentioned before, right? So its Hamiltonian can actually be written as a harmonic oscillator plus an anharmonicity, right? This 4th order nonlinearity in the creation and annihilation operators of our oscillators. Okay, and then we have our coupling Hamiltonian, which I've shown you before, to our mechanical modes, which are given by B here, right? And what we can do is, in addition, we can apply a drive to the system, right? And this results in an interaction that is often used, for example, in nonlinear optics and atomic physics, which is floor wave mixing. And that allows us to engineer interactions based on the frequency, let's say, of our drive that results in interactions between our qubits and our phonons and our microwave drive. Okay, so very briefly, one of the interactions that we can engineer, for example, is an effective interaction between different phonon modes, right? So basically what that involves is putting in 2 microwave drives whose frequency spacing is the same as the frequency spacing between the two phonon modes that we want to address. And again, due to this fourth order nonlinearity of our superconducting qubit of the Josephson junction, actually, what we can do is then basically make an effective interaction that allows our two phonon modes now to exchange energy. So remember, this looks similar to the native Hamiltonian between a qubit and a phonon mode, but now this is between two phonon modes, right? And this we can use if we turn on this operation for the right amount of time. We can perform what's called a swap operation, which again is like what I showed you before, where you take the energy in one phonon mode and you swap it into another. Okay, and using these kind of operations, we've actually proposed a architecture for using mechanical modes together with my collaborators in the group of Liang Jiao at the University of Chicago, of using these sort of operations to build something called a quantum random access memory. And again, this is taking advantage of the fact that we have so many of these individual modes in one sort of piece of quantum hardware, which is our mechanical resonator. And as you imagine, like in a classical RAM, a quantum RAM also requires many memory locations, right, to store its database qubits, and also to actually be able to route information about where we'd like to retrieve our information from. So I won't go into details about this, but the idea is basically that a quantum RAM acts like a classical RAM, except you can of course query and output superpositions of information, and it's actually a very important tool in a lot of quantum algorithms. Okay, and we showed that actually with the parameters of our system that we've demonstrated, especially with even slight improvements, we can get quite reasonable fidelities, for example, for our swap operation. Okay, all right. So just to finish up, I showed you how a circuit QAD system can maybe be used for storing quantum information. What I didn't talk about, of course, are all the other applications of such systems. For example, another unique aspect of a mechanical resonator is that it is a mechanical object and has mass, and so it can sense forces and other perturbations that are not available to electromagnetic modes. And it can also interact with other systems such as photons or spins, and there have been many ideas about using them as quantum transducers. Okay, and for that, what we're working on now is basically improving the parameters of our system so we can gain access to the full toolbox that will allow us to access these applications. Okay, and so these are some of the things we're working on in our group to improve these systems and perform new demonstrations using them. And when we're not doing that, here's a picture of us hiking in the lovely mountains of Switzerland. All right, so that's it. Thank you very much. I welcome any questions that you might have.
Thank you so much for this beautiful talk and amazing result. I'm extremely impressed. There is one question from the audience. From Yudi Zhang, I'm reading it. In order to propagate the infrared light through the antenna of hybrid quantum system using stimulated brilliant scattering to convert microwaves to optical signal, which kind of material is used in the antenna?
Yeah, well, so first of all, that's something that we would still be working on, right? Right now, there has not been a demonstration of being able to actually convert a quantum state fully from the microwave to the infrared regime, of course. So that's a huge goal for our field and something that we're working on as well. And so we are exploring different materials for that. And as you can see, because it's a hybrid system, it has to satisfy many constraints. Right, we have to find a good material for the piezoelectric. We have to find a good material for the mechanical resonator itself, and they have to have low microwave losses, low acoustic losses, and low optical losses. Right, so that really narrows down our possibilities quite a bit. And so, we're exploring materials. For example, so what we're using so far is sapphire, which is very good for microwaves. but are not piezoelectric, obviously. So we can put these other piezoelectric materials on top. However, for example, sapphire has a very low Brillouin response, actually. So it's not great, actually, for the optomechanical side of things. And so now we're actually exploring new materials. For example, things like the fluorides, like calcium fluoride, and other materials that are often used in optics, and trying to combine them with the right types of piezoelectric materials, which we're also exploring different types. So far we've used aluminum nitride, but many people in the community use things like lithium niobate, for example.
Thank you so much. I have another question from, I will probably not give the right name, Singlinde Flender. Sorry about that. Do you have to do anything special to prevent interference of external vibrations?
Yeah. So the nice thing about our devices is that they are at quite high frequency, quite high mechanical frequencies, right? So these are gigahertz modes of our mechanical resonator, and they're sort of, you know, these modes that involve differential motion of the atoms in a crystal. So if you think about it, there's actually not so many sources of mechanical vibrations that can excite a mode like that, and so we don't actually see. We don't really see any effects of external vibrations, although probably if we, you know, become better at measuring these states, maybe we will see that at some point. But for example, we've done experiments to measure that our mechanical resonators start very much in the quantum ground states of the mode.
Thank you. Another question from, oh, sorry. No, it was a compliment.
Okay, thank you.
I have a question myself. The first one is maybe you're working with phonons of exactly the same energy of the qubit, like you would do with the microwave. And it seems to me like with phonons, you have this opportunity to use acoustic wave of different frequencies and maybe have other possibilities. Like maybe it's a naive question, but you could use that you have very different scale of energy between your acoustic resonator and your qubit to couple phonons, qubits of different energies. Not work in a resonant regime, work in a completely different regime where you work with different energy scales. Is it?
Yeah. Sorry, go ahead.
No, is it something you think of interest or?
Yeah. So I mean, this is something that that people in the optomechanics community do. Of course, they use much lower frequency mechanical resonators, right? Yes. And that, of course, has its own usefulness. And the coupling is sometimes of a different form. The optomechanical interaction. There are the challenges. I guess you could try and use phonons of much higher frequencies, which I guess not many people have done. But at lower frequencies, the challenge there is for these quantum operations, you need to first cool the mechanical resonator to the quantum ground states, right? Which is more difficult. You can't do that by just putting it in a dilution refrigerator. But absolutely, I mean, people are using not so much bulk acoustic wave modes, but other mechanical modes at much lower energies. Yeah.
And another question, maybe, because I didn't know about this work where you generate n phonon Fock state. I mean, we are doing similar stuff in optics, and still struggling to see how useful it is for quantum information, because when you have more than one photon or one phonon, you're very sensitive to losses, and you don't like that. So I was wondering, in your community, because it's a very different community, how do you see this n phonon Fock state useful for applications?
Yeah, that's a really good point, right? So I mentioned that that there are all these proposals and schemes for using these states that have higher photon numbers, either Fock states or these Schrodinger cat states that I mentioned, for storing quantum information, right? But of course, as you mentioned, the main challenge there is that we're always fighting against decoherence and dissipation. And so there are various schemes for using quantum error correction, which is exactly for this purpose, right? For fighting things like decoherence. And that's really the main challenge, I would say, probably in all of quantum information right now. So absolutely, yeah.
And in the tiny last question on that topic, I mean, I don't know how to compare the dissipation for. I mean, you have now qubits which are coupled either to microwave or acoustic waves. And what I know from phonon is that you have more influence, in my opinion, to nonlinear terms. You have a large variety of anharmonic effects that dissipates phonons. I wonder if it's something that is a limitation or actually not a problem in your case? I don't know.
Yeah, so far we haven't seen that as an effect because we work with very few phonon numbers. So these nonlinear like scattering effects and things like that, right, scale strongly with the number of phonons in the system. And we're working very close to quantum ground state. We have, as you can see, up to say 7 phonons or so.
Yeah.
So the nonlinearities are not a dramatic effect so far, but that's actually something we're interested in exploring is whether or not if we can create bigger quantum states, right? If we actually start seeing nonlinear effects due to the anharmonicity of the lattice itself.
Okay, so I think we have to move to the next talk.
Great.
So
thank you so much.